Imagine you are watching a spaceship fall into a black hole. As it gets closer, something strange happens. The ship's clock starts ticking slower and slower. The astronauts inside move in extreme slow motion. And just as the ship reaches the event horizon, the point of no return, time appears to stop completely. This is not science fiction. This is a real prediction of Einstein's theory of general relativity. And it has been proven by experiments here on Earth. Welcome to Großdenken, everyone. Today we are going to explain exactly why time slows down near a black hole, and why the astronauts themselves would not notice anything unusual at all. Please support this channel by just subscribing. That would mean a great help. To understand why time slows down, you first need to understand what gravity actually is. Before Einstein, we thought gravity was just a force, like a magnet pulling objects. But Einstein showed something far stranger. In general relativity, gravity is not a force. It is the curvature of space-time itself. Massive objects like stars and black holes literally bend the fabric of space and time around them. And when space bends, time bends with it. The stronger the gravity, the more space-time is warped. And the more space-time is warped, the slower time flows compared to a distant observer. This is called gravitational time dilation. Here is the key fact. This is not theoretical speculation. It has been measured. Atomic clocks at the top of tall buildings run slightly faster than clocks at ground level, because gravity is weaker higher up. GPS satellites have to constantly correct their clocks because time runs faster in orbit. Near a black hole, gravity is so intense that the effect becomes extreme. At a specific distance from a black hole, called the Schwarzschild radius, something mathematically dramatic happens. Time dilation becomes infinite. The formula for gravitational time dilation is straightforward. The closer you get to the Schwarzschild radius, ORS, the slower time moves compared to an observer far away. At the Schwarzschild radius itself, the event horizon, time essentially stops. This is why black holes were once called frozen stars. From the perspective of an outside observer, infalling matter never actually crosses the horizon. It appears to freeze in place, growing ever redder and dimmer until it fades from view. But here is the mind-bending part. That is only what an outside observer sees. If you are the one falling into the black hole, time appears to flow perfectly normally. Your clock ticks at its usual rate. You feel no time dilation at all. You would cross the event horizon without even noticing it, except for the tidal forces that would eventually tear you apart. In fact, from the falling astronaut's perspective, the outside universe would appear to speed up tremendously. They would watch billions of years of cosmic history flash by as they approach the event horizon. This is the core lesson of relativity. There is no absolute time. Time is relative to your motion and your position in a gravitational field. Both the outside observer and the falling astronaut are right about their own experience. You might be thinking, that is fascinating, but is it actually real? Yes. We have measured gravitational time dilation with extraordinary precision. In 1976, NASA's Gravity Probe mission launched an atomic clock to an altitude of 10,000 kilometers. It found that time passed faster in space by about 40 microseconds per day compared to Earth, exactly as Einstein predicted. Every time you use GPS, you are relying on this effect. The satellite's atomic clocks run faster due to weaker gravity, and they must be constantly adjusted to match Earth clocks. The movie Interstellar dramatized this brilliantly. On a planet close to a black hole, hours passed, while decades elapsed on Earth. That is not Hollywood fantasy, That is physics. So why does time slow down near a black hole? Because mass curves space-time. Near a black hole, the curvature is so extreme that time itself stretches almost to a standstill compared to distant observers. And the most profound lesson? Time is not a universal clock ticking everywhere at the same rate. It depends on where you are and how strong the gravity is. That is the strange, beautiful reality of Einstein's universe. Next time you look up at the stars, remember, every clock in the universe ticks at its own rhythm, shaped by the gravity around it. And near a black hole, that rhythm slows to almost nothing. That is the mind-bending reality of general relativity. Thanks for watching, and hit subscribe for more deep dives into the ideas that shape how we understand reality.